Got it. Okay. No, thank you very much for this opportunity to talk about one of my favorite topics in stellar astronomy. And as you can guess from the title, today I'm going to talk about what stars eat for dinner. So basically planet engulfment events, and more specifically planet engulfment events in sun-like stars. This is not only interesting by itself, but as we will see later, it is somehow related to many other very intriguing topics, including, for example, the search of true analogues of our solar system. So usually when I talk about planet engulfment events, I start with this famous diagram, which describes the demography of the exoplanet population. And it clearly shows that one of the most interesting discoveries over the short history of exoplanet science is that although planetary systems are very, very common in the galaxy, most of them are quite different from our solar system. And most importantly, there are also big differences among themselves as well. So this big diversity is probably the result of severe dynamical processes that have imposed the significant reconfiguration of planetary system architectures. So it's possible that in the most dynamical systems, part of the planetary material may also have fallen into the hosting star. And the knowledge of the frequency of planet engulfment events in sun-like stars will shed light on the possible evolutionary path of planetary systems, but also on the rate of orderly systems similar to our solar system. So I know that there are many astronomers that are tackling the same questions with complicated N-body simulations or collecting data from planetary systems. However, the results that I'm going to present are also important because they allow us to study the same topic, but from a completely different perspective. So not the perspective of the planetary system, but the perspective of the hosting stars, of the hosting star. So, but why am I talking specifically about planet engulfment events in sun-like stars? Because in the recent and less recent literature, high-precision spectroscopic studies have unveiled the chemical anomalies in stars that have been interpreted as the result, or if you want, as the consequence of planet engulfment events. Here, for example, it is shown the differential abundance between two components of a binary system, of this binary system, as a function of the condensation temperature. So while the two stars look very similar in the volatile elements, the volatile elements are the elements that prefer to stay in a gaseous phase, like oxygen or carbon. The northern component here, so this component, is significantly richer in refractory elements, which are the elements that easily condense and form rocks and planets. The solid bodies of our solar system are mostly composed by refractory elements. So cases like this represent one of the strongest points of friction between theory and observation in stellar astrophysics. In fact, we know that stars that form within the same stellar association, they should be chemically identical simply because they form from the same cloud, they form from the same, at the same time, from the same material, so they should be chemically identical. Instead, we observed cases like this. So in this case, it's possible that the northern component has engulfed a planet which polluted the external convective zone of the star, changing its composition of refractory elements. However, there is no proof of that. This is just an hypothesis. There are other explanations. For example, it's possible that the two stars formed from a cloud that, for any reason that we don't know, was not very well mixed, so that the two stars formed with a slightly different composition. So you understand that we must resolve this ambiguity, because this is not the only case. There are many other binaries composed by sun-like stars that are showing a similar chemical anomalies, which may indicate that planet engulfment events are quite common or not. So That's why we carried out an experiment that for the first time clearly indicates the cause of these chemical anomalies. Okay, so our experiment is very, very simple. It is based on two very simple phenomena, which are pollution and dilution. So imagine that you have three sun-like stars with a slightly different temperature. So you have the colder one that has a thicker convective envelope, while you have the hottest with a thinner convective envelope. And now imagine that you throw planets onto these stars. So the planetary material will be completely diluted for the colder star because of the thicker convective envelope. So this material will not be able to produce any significant change of the stellar composition, but it will be able to significantly increase the abundance of refractory elements for the hottest stars. So if the chemical anomalies that I showed you earlier are really due to the external pollution of rocky material, then the probability of finding chemically anomalous stars should be function of the stellar temperature. So this is this very simple hypothesis that we want to test. For this experiment, we used a sample of 107 binary pairs composed by sun-like stars. These binaries are composed by stars with a very similar temperature and gravities, and also these stars have a convective external layer that can be polluted. And we divided these pairs into classes. We have 74 chemically homogeneous pairs, which are defined as those whose components have a similar iron abundance within 2 times of the associated uncertainty. And we also have 33 chemically anomalous pairs, which are composed by stars with a different iron abundance. Okay, so in this plot, I'm already showing some results. Here I'm showing the 107 pairs as a function of the mean temperature of their components. I have divided the chemically anomalous pairs from the chemically homogeneous pairs, and you can already see by eye that the chemically anomalous pairs are preferentially located on the left side of the diagram. However, we can use these observations to model the probability of finding chemically anomalous pairs as a function of the temperature. So for this model, we have used a sigmoid function that is an animal that looks like this one here. The important parameter is the beta parameter. So the beta parameter is the one that sets the type of relation that exists between the probability of finding anomalous pairs and the temperature of these pairs. So the important thing is that the prior for the beta parameter was set to a normal distribution centered on 0. And we clearly see that our MCMC simulation has selected positive values for the beta parameter, giving a positive relation. So more precisely, the solid line is the observed average posterior, while the shaded area is the 90% confidence interval of the posterior solution. So now, given this result, we can clearly see that the probability is higher for the hottest pairs, and it's near 50%. So it's the probability of finding anomalous pairs is near 0.5 for the hottest pairs. So assuming that the hottest stars change their composition at every planet engulfment event, and assuming that at least one star of the anomalous pairs has shallowed a planet, we can derive the probability of planet engulfment events among sun-like stars, which result to be 0.27 with this 90% confidence interval, which is quite high compared to what we were expected. We also developed a model produced by a mock data set of 500 binary pairs whose stars range within this range of temperature. We randomly polluted 27% of these stars with an amount of planetary material that was randomly drawn from this normal distribution. And then we repeated the MCMC simulation, and these are the results for different metallicity. we can see that this experiment match very well with our observation. So I'm not saying that these stars, our stars, have been polluted by this amount of planetary material. This, unfortunately, is impossible to tell, but I'm just saying that our observations are perfectly consistent with what you would expect from planet engulfment events. But when did this planet engulfment event happen? So this is an important question, because the fall of rocky material into the central star is something that actually is normal during the phase of planet formation, or even a bit later when the planets are already formed, but they are still clearing their orbits from the debris of the protoplanetary disk. So we know that planets typically take a few million years to form. We also know that circumstellar disks are completely dissipated within 10 million years at most. And we argue that the chemical anomalous that I've shown you earlier have been imprinted by planet engulfment events occurred later in time. So when these disks are already dissipated and the planetary system is completely formed. And this happens, this is because young suns have a very thick convective zones, so when they are young. So any material that they can possibly accrete when they are younger, let's say than 10 million years, will be completely diluted. Instead, the convective zone shrinks as the star gets older and older. So we expect to see the chemical signature only when the star is older than 10 or 20 million years. For example, in this diagram, we see the mass enclosed in the convective zone of a sun-like stars divided the mass of the entire star. And we can see that when the star is very, very young, 5 million years, it's basically entirely convective. The convective zone is huge, it's very, very deep. Instead, when the star is a bit older, the convective zone is much thinner. Sorry. So in this diagram, we see the conditions to produce an increment of iron of a 0.04 dex, which is something similar to what we actually observed in our binaries. So for a 20 million years star, you just need a 1.5 Jupiter masses of a planet that has this ratio of metals over hydrogen, which is something that we can assume normal for a planet. So you just need 1.5 Jupiter masses to produce this variation of iron. But when the star is much younger, let's say 10 million years, you need 9.5 Jupiter masses, which honestly is a bit too much. So what I'm saying here is that the phenomena that, so this dramatic event of planet engulfment events that I showed you earlier and that we are detecting occurred after the formation of the planets. And can we say something more about these anomalies? Of course, yes, we can, because I still have 10 minutes to talk, I think. So, for example, let's say that we have an anomalous pair. So these are two stars in a binary system, and this binary system is anomalous, and we have the metal-rich star, and we have the metal-poor star. So the question is, among these two components, which is the anomalous star here? Is it the metal-rich one, which is anomalously richer of metals? Is it the metal-poor one, which is anomalously poorer of metals? Or instead, are they both chemically anomalous? So to answer this question, we compared the iron over carbon abundance ratio of the two stars to the typical values that we see in solar twin stars. So solar twins are stars that are very similar to the sun in terms of temperature and gravity. So why iron over carbon? Because this abundance ratio is a proxy for the abundance ratio of refractories over volatiles. So, and also for this comparison, we also have taken into account the metallicity and the age of these pairs, so that we don't compare apples to oranges. So in short, if this is the distribution of solar twins. We can assign a high percentile rank to a star that has, let's say, this value of abundance ratio. And this high percentile rank means that the star has an abundance ratio that is higher than expected. While if a star has this abundance ratio, it will have a low percentile rank, meaning that the star is a refractory volatiles ratio lower than expected. And we have calculated the percentile ranks for all the components of the anomalous pairs. And this is the result. So while the metal poor stars cover in blue here, cover a wide range of percentile ranks, meaning that they are not anomalous compared to what we see for solar twins, we clearly see that the metal-rich stars preferentially have a higher ranks, meaning that their abundance ratios are higher than expected. So this is a strong indication that the metal-rich components of the anomalous pairs are those that are anomalous. So they are the stars whose chemical partner has been somehow changed. And this is another strong indication of that the anomalies that I showed you earlier are the smoking guns of a planet engulfment events. Okay, and finally, what I call the lithium test. So lithium is a strange element because it is depleted in stars at different rates, in sun-like stars, at different rates depending on the stellar mass. As we can see from this nice diagram from Marilia Carlos, so this is the abundance of lithium as a function of the stellar age for a bunch of solar twins. So all stars and all planets are formed with the same amount of lithium in their atmospheres, but the lithium abundance decreases only in the stellar atmosphere as time goes on, simply because it is burned into the stellar interior. But planetary material, of course, retains the original supply of lithium. So I'm putting this plot here to show you that is quite easy to say if a star has or does not have a lithium in its atmosphere. These are two stars of our sample, and you can clearly see that the lithium, if the star is young enough, is quite deep, while if the star is old enough, there is nothing here. Okay, so going back to our lithium test, when a star has no lithium anymore and it's a planet, then the atmosphere should get refilled of the lithium that was carried by the planet. So it should appear significantly richer than its companion. And this is the other simple hypothesis that we want to test. We think that in some cases, an anomalous overabundance of iron should come with an anomalous overabundance of lithium. And we tested this hypothesis on a subsample of pairs for which we have been able to derive lithium abundances, and also pairs with very, very similar masses, whose components have very similar masses. And the hypothesis turned out to be verified, as we can see in this diagram, which shows the differential iron abundance of the two components for each binary pairs. The iron of the second component minus the iron of the first component. And here we have the same for lithium. And you can clearly see that while the homogeneous pairs are homogeneous in iron and also more or less in lithium, the story, with the only big exception here, the story is completely different for the chemically anomalous pairs. And we observe that for these anomalous pairs, there are cases where the star with a higher abundance of iron also is anomalously overabundant in lithium. Okay, so coming to the conclusions, this is a short recap of our main results, and then we will see the next slide with some important implications. So we provide three important pieces of evidence indicating that planetary engulfment events can happen in sun-like stars. We have shown that this dramatic event can change the chemical pattern of the stars in a very well-defined way, and in a way that we can detect. We found that the planet engulfment events are quite frequent around stars similar to our own, so that a non-negligible fraction of planetary systems around sun-like stars have experienced an extremely dynamical past with the planetary engulfment events. And then I would like to stress that our method of analysis is totally independent to the other method of analysis that are usually employed to address this type of questions. So, for example, we are completely independent from both exoplanets detection techniques or N-body simulation. And this means that our results can be directly compared to the results of that will come from this other technique. And then this is the last slide. I would like to conclude putting our sun in the context of our research. Unfortunately, the sun does not have a companion that can be used as a reference star to define whether the sun was polluted or not by rocky material. So the best that we can do is to consider the chemical composition of other stars close to us. This has some dangers because, of course, if we observe today a star that is very close to the sun, it does not necessarily mean that it formed in an environment that was similar to the environment where the sun formed. It could have formed at a very distant location in the galaxy and then migrate here. So this has some dangers, but this is the best that we can do at the moment. So in this diagram, we are showing the refractory over volatiles ratios for a sample of 80 solar twins that was analyzed at very, very high precision. And we can see that the sun has a low percentile rank, let's put it this way. It's a low ratio of refractory over volatiles ratio compared to the other solar twins. And this result holds also if we correct the chemical pattern for the galactic chemical evolution. And we also see that the sun lies in the lower boundary of the lithium versus age distribution of solar twins, which means that probably the sun is slightly less abundant in lithium than what we would expect compared to the other solar twins. So the question is it that related to the architecture, to the quiet and ordered architecture of our solar system? We know that our solar system has an architecture that is very calm. The rocky planets are located in the inner regions, the gaseous planets are located in the outer regions, or planets are on nearly circular orbits. So it's possible that the sun has never engulfed a lot of material. And it's also possible that most of the other stars have engulfed a lot of planetary material. We still don't know that. So that's why I think that the most important question that we have now is the following. Can we use the chemical composition of stars to identify those with higher chances of hosting true analogues of our solar system? So this is a really important question because imagine even with the better instruments and the better techniques of analysis, the search of twins of the Earth around the twins of the sun will always look like searching for the proverbial needle in the haystack. That's simply because we have so many stars that you can possibly target. So having an easy criterion to get some high priority target will make things much, much easier. And then I would like to conclude with this bullet here. So we are currently preparing the next generation spectroscopic surveys, and these surveys will dedicate a significant fraction of the observing time to observe stellar associations like binaries or clusters. So this provides the perfect opportunity to study this topic in more details and hopefully to find an answer to this question here. Okay, I finished, so I'll take your questions.